Okay, thank you very much. Thank you to the organizers. Sorry, I have to wake up my English as well. Yeah, it's always a pleasure, a really great pleasure to be in London and with you. So, okay, so my presentation will be about a recent work with Johannes Muhle-Karbe from Carnegie Mellon. It's about small transaction cost and how you approximate utility maximization problems with small transaction costs by utility maximization problems without transaction cost. And there have been a lot of work on that. I will give you some of the references, old works and more recent works in the, let's say, last 4 years. And the point of this work with Johannes is that all these works are quite technical with quite a lot of assumptions and things like that. And then when you discuss with people why the result should be that, I will give you the result in a minute. Why the result should be that, they tell you stories. Well, it's blah, 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 because of this, because of this. But then when you look at the proof, they are never doing what they tell you. It's quite surprising. So finally, with Johannes, we said, okay, let's just take their words and try to write it down. And what I will present you is actually this. You can actually write down exactly what they tell you. It's not difficult, and it gives a very short proofs for at least upper bounds that you can find in all these papers. So our results will be slightly more general than what was done, at least on one direction. But the important thing for me is also that maybe now you can tell the story to master student programs, because with a level of M2, you can actually do the proof within, let's say, 2 hours or so. It's really not difficult. Okay, so the story is this. For those who don't know this, so I will take a stock market. Yeah, one point. From the practical point of view, this has implications, okay, because what we do in this literature is consider a model with transaction costs. So you have a model, a market with frictions, okay? And when you do portfolio management, portfolio optimization, adding transaction cost into the picture makes the computation quite difficult, okay? And the idea of all this work is to say, well, if transaction costs are small, then we should not be far from the case where there is no transaction cost, for which you can even maybe opt to have explicit solutions, so no numerical problems. And all the question is how you should deviate from the optimal policy in the model without transaction cost to obtain something not far from being optimal in the model with transaction cost. So in terms of applications, this is really something important. It's kind of model approximation, if you want. Okay, so I have a stock market with d-dimensional continuous semi-martingale S. This is stock price. It doesn't need really to be continuous, but I will later on consider strategies that are somehow continuous. And if the stock price are not continuous with the optimal strategy in a utility maximization problem, will certainly not be continuous. Okay, so let's make it continuous right from the beginning. And then I will compare a frictionless market where your wealth process, so I don't take care of interest rate here. You can obviously add it as usual. So your wealth process is your initial wealth plus the gains you made from trading, where theta, each of the component of theta denotes the number of stocks you have in your portfolio at the different times. Okay, very simple. Okay. Then let's consider a market with transaction cost. So this formulation here is not the, well, it's, you have different formulation, one that is more common. This is not the more common one, but I will come back to this later. So here transaction costs, so you can trade the similar way on the stock. And now you pay a transaction cost with the factor epsilon on the number of trades you make. Okay, so var theta here corresponds to units of the asset you have, okay? And each time this guy moves, so it increases or it decreases, then you pay a transaction cost. Okay, so the transaction cost is on the number of stocks that are traded. Okay, what is more common is to put transaction cost on the volume in terms of money that is traded. But we can do it very similarly. It turns out that this formulation is simpler to present. Okay, so var theta here, this is just a predictable process. Now var theta, because here you have the total variation, it has to be a process with finite variation. Otherwise, well, if you trade too often, you will just go to minus infinity very quickly because you pay transaction costs each time you trade. And here, This term is for final liquidation. So you look at your position, the number of stocks you have, you liquidate all your stocks in cash, okay? And this is what you will have. So this guy here is actually the money you have in your portfolio, okay? So this is a money account, the cash account, and the number of stock is in Varsita. Okay, and what you want to do is, well, typically to compare these two guys, I give you a strategy in the model without transaction cost. How close can I be with the strategy in the model with transaction cost? So how close can I make this guy from this guy? So you can look at this in LP norms, in different, well, norms or criteria. And we are particularly interested in that criteria. So here we want to compare, actually not given a strategy, but we will maximize the expected utility in a model without transaction cost, and we want to compare this quantity with what we can gain in the market with transaction cost. Okay? And from a practical point of view, the idea is that for that problem, it might be not so difficult to solve, even explicit. For instance, if you are in complete market or in certain incomplete markets. For this one, you have to, in the Markovian setting, you will have to solve variational PDEs. This is quite involved if you are in high dimension. So maybe you can use the optimal policy that is taken from there, put it in here, okay, deviate a little bit from this optimal policy and obtain something that is almost the supremum in the model with transaction cost. Okay, this is a practical application. And you will see that I will show you how you can actually do this approximation. Okay. Now, what are the expected results? So, if I give you a strategy here, and you want to construct a strategy Varsita in the model with transaction cost such that these two guys are close by some criteria or another, what you will typically do is say, okay, let's put a bandwidth around this guy. So you have the strategy theta, you put a small bandwidth around it. And, well, what you have to balance is actually, well, if you are far from the theta I gave you, then let's go back to the dynamics. It's actually simpler. If you are, if Varsita is far from this theta, then you will have a loss due to the stochastic integral. Okay, you have a loss of control, so you will lose something. On the other hand, if you try to have this Varsita too close from this theta, then you will have to transact a lot, and you will pay a lot of transaction costs. So the story is, well, how do I balance these two terms? I want to stay close, to have these two stochastic integrals quite close. But on the other hand, I don't want this guy to move too much because otherwise I'm losing money with transaction costs. And all the idea is to balance these two terms and to tune them such that, well, the contribution of the two is the same, basically. Okay. Now, if you say, for instance, so you give me theta in the model without transaction cost, and I tell you, okay, let's stay at a distance delta of theta. So var theta has to stay at a distance delta of theta, okay? So I look at the square root problem, and I know that whenever I will reach the boundary, theta plus delta or theta minus delta, I will have to transact, and this will be related to a local time, say, of a Bruno motion, if you want. And typically, remaining at the distance delta of this guy theta will have a cost of order in total variation. The total variation, so what I will pay in transaction cost will be proportional to 1 over delta. So I will pay epsilon over delta transaction cost, basically. This is the idea that everybody has in mind. So coming back to the dynamics, if I just say, okay, let's have this guy just staying at the distance delta of this one. Here I will have this guy of order 1 over delta, so I will pay epsilon over delta in transaction cost. And then, well, the difference between the two, theta and var theta, will be less than delta, so you can estimate the difference between the stochastic integrals. Now you match the terms in LP or whatever for the moment. You take the delta that is optimal with respect to epsilon, and you get an estimate for the tracking error. So for the LP bound, if you just do this exercise, using this rule here, this is very simple. LP bound will be of order of a constant to multiply by the level of, well, the coefficient of transaction cost to the power 1/2, which is very good. This is in any LP. And this is achieved just by taking a distance delta that is of the order of root square of the level of transaction cost. For utility maximization, I have to write down things because this is a little bit, I mean, you have to see really the contribution in more details. I cannot explain it just by waving hands. But basically, this is not so much difficult. And this time you have to take delta of order of epsilon to the power 1/3, not a root square of epsilon, and the difference in expected utility. So here you will track the optimal strategy here. The difference in expected utility will be what people know and have in mind, that is of order of epsilon to the power 2/3. Okay, so this is really the story that people tell you. Let's stay at the distance delta, you pay in local time 1 over delta, you match the terms, you have this. But it's never written like this, actually, in the proofs. So here is a part of the literature. Actually, this kind of study, so small transaction cost expansion, goes back to a paper of Shreve and Sonner. It's a little bit hidden in the paper, and it's an old paper, so maybe it has been a little bit forgotten. Then obviously there is Wallet-Wilmot that really makes this more popular. And then all the work around Shreve. There is, a paper also by Rogers where he explains again the idea I just gave you, but with just waving hands. And more recently, we have all the work of Bichouche, that is for power utility. So all this work are basically in the Black-Scholes model with power utilities, things like that. Okay, so it's not that they have heavy assumptions; it's that the model is Black-Scholes with power utility. So just assume that the volatility is strictly positive. This is the only assumption you make. But okay, it's really in one particular case. And then it was kind of industrialized by Sonner and Tuzi, together with Posamai and other people, including me, actually, and Johannes, and also Ludovic Moreau, and other people. There have been a lot of work after the paper of Sonner and Tuzi, where what they do is use homogenization techniques. So it's different PD techniques. What they have to do in this work is essentially assume. Let me go back. Whoops, that's the problem when you, They have to assume that this is true. Okay, the sup of the difference is of order of epsilon 2/3. Okay, they assume this right from the beginning in the paper. Then they check it in certain cases, but very particular cases. But, okay, let's assume that. And they tell you if you assume that, then you take, you use homogenization techniques and viscosity solution techniques. You can actually derive PDE for two PDEs actually that are giving you the exact first order term in the expansion of the difference. Okay, so if I assume that I have the good rate of convergence, then I use this homogenization technique, and I can give you the expansion of the difference, and I can characterize exactly very precisely what are the leading terms. Okay, they are a solution of what is called the first order and the first corrector and the second corrector equation in the homogenization literature. So this was also a motivation for this work, because in this work we will prove this in a quite general setting. Not that general, but you will see, okay? At least in cases where they were not able to prove it. So we'll prove this, and once we have proven this, we just use their technique, up, we have the expansion, the exact expansion. Okay, yes, this is what I said. So their approach is kind of really industrial machinery. It's systematic, but you have to assume that you have already the good rate of convergence at first. There are also some regularity condition on the corresponding Morton problem, so the problem without transaction cost. The Hamilton-Jacobi-Bellman equation has to have a smooth solution. And here they have, I mean, I'm fine with that. Where I'm not fine in their assumption is that they have bounds on gradient up to the time boundary capital T, which is very difficult to prove. I mean, interior regularity is fine. On the boundary, usually it's exploding. I will comment this later because with our approach, we can actually remove their terminal, their bounds on the boundary, just because they essentially have to prove something like that. They have to prove that if I take the sup of the difference and I divide by epsilon 2/3, so let me put it differently. They have to prove that this constant C goes to 0 when the time to maturity is going to 0. This is where they have very heavy assumptions. Actually, you will see in the proofs that the constancy is time dependent, and without too much assumption, it will be very easy to check that it's going to 0 when the time to maturity goes to 0. So we don't highlight this in the paper, but it's a byproduct of what we do. So I guess it really coupled with Sonner and Tuzi's approach, well, you can do a lot. Okay, these are for the PD approach, and you have also the probabilistic approach, shadow price and based on shadow price and duality, initiated by Carlsen and together with Johannes. Then there is a paper with Gerold, in the et al. You have Schaschermeyer and people like that. Okay, so all these are very nice works, but quite complex. And again, the aim of my presentation is to show you that, at least for giving the correct order, this is very, very simple. Yeah, there is also a very interesting paper by Kai, Rosenbaum, and Tonkov. But here they are doing tracking of the frictionless model, but in probability. So it's a different approach. But this is a very, very nice paper. Okay, so the general idea, again, is to balance between deviating from, well, theta hat, that would be the optimal strategy in the model without transaction cost. So you don't want to deviate too much from it, and still you don't want to pay too much transaction cost. So you have to balance these two terms. And, yeah. So what we do, again, I already said that, we just do this, and we will take simplest transaction cost region as possible. So we'll just take theta hat plus delta. In the other papers, you actually put time-dependent and space-dependent functions, and you have to tune it. Either you read it from PD's, first corrector or second corrector equation in the homogenization literature. You construct it by hand. Sometimes you want to take the one that should be optimal, but it doesn't work, so you twist it a little bit, and at the end you have the result. You have to do complex things. Here I will just take the guy plus or minus delta. I don't care. Okay? Then if you do this, actually the L2 error, this is 2 lines. The tracking error in L2, this is really 2 lines. For utility maximization, we will stick to the case where the utility function has bounded risk aversion. And in that case, you can use a trick that we already use in a paper with Ludovic and Romel Dely. Well, I don't want to discuss this paper. But if you use this trick, then you do the utility maximization problem in 4 lines. Okay. So, and this will give the simple proofs. Okay. Yeah. The main limitation is that it is limited to bounded risk aversion. Yeah, it can be more general. I will comment on that later. In the paper, it's limited to this. Okay, so let's go to the LP bounds first, because anyway, this is an input for the case of utility maximization. So as I told you, we just do the simplest thing. I pick up a constant delta, and I say, okay, you give me a strategy in the frictionless model, and I consider the bounded variation process such that the difference is staying in minus delta plus delta, okay? And I do it component by component. So the shape of the square root problem is very simple. This is a square. So I will write things in dimension 1, because at the end you will just have to look at each of the dimensions and sum up the terms. Okay, so this is a square root problem again. I look at var theta such that I stay in that domain, theta minus var theta, and this guy should move only when I reach the boundary, okay? So I transact only when theta minus var theta is equal to minus delta and delta. So I don't know if you know that, but if you want to control the total variation of these guys, this is very well known actually. So it's particularly known for, well, people that have worked on the square root problem, but also by people that have worked on reflected diffusions, reflected SDs, and there is no, in particular, maybe the most general work is by Dupuy and Ishii, where they find a way to control this guy to prove the existence of reflected SDs in quite general domains. So here what we use is the basic thing, and there are much more general things. So here what we have to do is to take a test function. So I take a function phi, And I just impose to phi that the first derivative at point -1 is -1, and first derivative at point 1 is 1, and I want it to be bounded together with its derivative. In more general cases, you have results where you need to use a test function like that, but typically in Dupuy-Ishii paper, you don't know the test function. They have a whole paper showing that there is a certain function that is having a certain number of properties, okay? Which are a little bit more complex than what I've write here, okay? These are for domains that have a complex shape. Okay, so here you take the very basic one. Derivative as -1 is -1, derivative at 1 is 1. Okay. Then I rescale theta minus var theta to reduce to be in -1, 1, so I just divide it by delta, and I call this guy z, okay? And then what I will do is just apply Ito's lemma, and this will give me in 2 lines the control on the total variation of var theta. Okay, this is something that is well known, this idea. So z again is theta minus var theta divided by delta. I apply Ito's lemma, so phi zt is phi z0 plus, okay, so I have the first derivative. So this is a variation of theta minus var theta divided by delta, because z is the guy divided by delta. And then I have the second order term, so I assume here, yeah, I should have said this. I assume that theta is a continuous semi-martingale, okay? And then I have the bracket term related to theta. Again, var theta is a bounded variation process, so there is no contribution from that side. Okay, now the trick is this. The derivative of phi is 1 at 1. Okay? So when z is 1, this means that theta minus var theta is 1. This means that theta minus var theta is equal to delta. Okay? Theta minus var theta is equal to delta. So you have actually to have a variation of var theta that is negative, okay, to stay in the domain. Okay? So when z is 1, when this derivative is 1, this means that d of var theta is negative. Okay? At the opposite, when z is -1, d of var theta is positive for the same reason. This is exactly the same. So when d of var theta is positive, this guy is +1. When d of var, sorry, the other way around. When d of var theta is negative, this guy is 1. When d of var theta is positive, this is the other way around. And I hope I gave it in the good, yes, in the good sense. Anyway, at the end, phi prime, because of this property, phi prime d of var theta will give you exactly phi prime d of the absolute of the total variation of var theta, and phi prime when var theta moves is equal to 1 in absolute value. Okay, so you will get exactly. So this term here is exactly the total variation of var theta. Maybe I did it the other way, but this is the idea. Okay, anyway, so now it's easy. I mean, you just put var theta the other side. Okay, this guy is bounded by 1. This guy is bounded by 1. Phi prime is bounded by 1. Well, you don't know what theta is exactly, but this guy, you know that it is bounded by 1, so this guy cannot be too nasty. And phi second is also bounded by 1. So, for instance, this guy is bounded by just the total variation of the bracket of theta. And this is what you get. So here I will always use this notation. B1 is the set of adapted processes that are bounded by 1. Okay? So I put var theta the other side. You have it here. So the D here is for the dimension. I got back to dimension D. Okay? So actually forget about the D. D is 1 for the moment. And you have 2 delta. 2 delta comes from 1. Well, bounded by 1, bounded by 1. The difference of the 2 is bounded by 2. Okay? And the delta that is in front, this is because the total variation is divided by delta. So when you put it the other way, you get 2 delta. So again, the 2 is this one and this one. This term here, well, I told you that this guy is bounded by 1, so it's a certain process bounded by 1. And this guy is bounded by 1, so this guy here is bounded just by the bracket. Okay? So now, obviously, you have to make assumptions. I mean, well, you don't know exactly what this guy will be, so this is the bound we have. You don't know exactly what this guy will be, so let's say that I pick up probability measure Q, some P, well, it doesn't need to be, well, say bigger than 1. And I will just assume that the LP norm of this guy is bounded uniformly over processes size that are bounded by 1, so it's close to the Emery topology, I think, but without the inf1 term. But it's related, so it's kind of topology on semi-martingale that I'm putting here. I have to well assume that the bracket of theta is also bounded, otherwise I won't have a bound for this one. So if I assume that I have such bounds that do not depend on epsilon, obviously, they just depend on P, well, no, on delta for the moment, I don't need epsilon. Then, well, if I pick up a delta between 0 and 1, less than 1, just to forget about one of the terms, the term here, well, I know that the total variation of var theta in this norm is less than, well, a constant that depends on P, slightly different from this one up to small terms. And this is of order 1 plus 1 over delta. Okay, so this is what I told you. The total variation related to of the term you have in the square root problem should be of order 1 over delta, and this is what you find here. So yeah, again, this is actually quite well known, these techniques. And the 1 over delta, just if you want again to check, you cannot really avoid it. So if you do exactly the same computations, but now you say that, for instance, theta is a cube random motion, if you pick up the function phi, that is z squared over 2, at least in minus 1, 1, the computation I did before taking inequalities, so the stochastic integral part will disappear because theta is a Brownian motion, so I just have this term remaining. And you see that in L1 norm, the total variation is actually, well, so this guy is bounded from below by minus, why do I have minus 1/2? Yeah, okay. Yeah, because this is phi like this. Okay. So this term here for delta less than 1 gives you lower bound minus 1/2. And then the 1 over delta term is just here. The t here is just a bracket of theta, which is assumed to be a Brownian motion. Okay, so you get 1 over delta. Okay, so you cannot improve this this bound. Okay, this has to be 1 over delta. Okay, so tracking in LP is very simple. Estimating the total variation of the process var theta when you use this very, very simple rule is actually very simple. And now if you look at the difference of the Wells process, it's quite simple as well. So I just wrote down the difference of the two Wells processes. I have the stochastic integral part with respect to stock price, and then I have the transaction cost part. Okay. Now I know that I have taken var theta such that the difference of the two is less than delta. So this guy is actually a term that is living in minus 1, 1. Multiplied by delta. So this is living in minus delta delta. Okay. So I rewrite it like a guy living in minus 1, 1 multiplied by delta. Okay. So this is just this. And I just gave you U per bound for the total variation of the process. I put a 2 because I U per bound this by the total variation of the process at time capital T. Okay. This is where I have a 2. So 2, this guy plus this guy, times epsilon, and then the bound I have on the total variation that is given by the formula I just gave you before. Where again, the x's are always guys that are living in minus 1, 1. And then again, you have to make assumptions anyway if you want to have LP bounds. So now I assume that the sup of our processes living minus 1, 1 of this stochastic integral in LPQ is bounded by a constant. And if I assume that, well, the tracking error I get by following this rule is delta, this assumption, this gives me a constant, okay? And then 2 epsilon, and what I got from that term before, which is of order 1 plus 1 over delta. Okay, so it's 2 lines again. Now, how do you choose delta? It's clear. Well, you have delta, here you have epsilon over delta, you want to make them of the same order, and the way to make them of the same order is to take epsilon of order of delta squared, which means delta of order of epsilon, root square of epsilon. And you get the the tracking error you want. Okay. Okay. If now you take again just to see that you cannot do much better. Imagine that again theta is a Brownian motion and S is an isothermy martingale with good coefficients. Here this is a drift of the process S. If you just redo the computation I just showed you, and you take the expectation of the difference, you will end up with these terms. Okay, so you see the contribution delta here. You see the contribution epsilon over delta here. Okay, and here you have a upper and lower bound that are exactly of the same kind. It's always delta, this term, and minus only the constant is changing here. Okay, C and C prime. This is just a question of constants. These are exactly the same terms up to constant. Okay, and now, well, unless this guy disappears, okay, unless this guy disappears, you see that the upper bound and the lower bound always exhibit delta and epsilon over delta. So what I gave you before is sharp. Okay, we cannot do better again. Up to constant. In particular, so in general, you cannot do better. And what I wrote here, you cannot do better unless this term disappears, okay? Unless this term disappears. And when I will do utility maximization, the measure Q will actually make S a martingale. Okay, so this term will disappear. Okay, so for the utility maximization, for the LP tracking, if you are not under a martingale measure, you cannot do better in general. But for utility maximization, this tracking will be done somehow under the martingale measure. Okay, so I will just use the bounds corresponding to the other terms. Okay, and this explains why you don't take the same delta in the utility maximization problem as in the tracking error problem. Okay, in the utility maximization problem, you don't have this contribution. In the tracking error, you have it in general. Okay, so now how do you do for utility maximization? So again, we need to make assumptions. I will explain how you can generalize it. The major assumption we make here somehow is that the utility is defined on the whole real line. When I quote the other papers, most of the papers are about power utility, so we do not treat this case. Okay, so utility maximization has to be done on the whole real line. We don't want to have to care with cutting the wells when it goes negative, or, well, it might go negative. Okay. Then this framework with bounded risk aversion is a nice framework because you can really write things, simple things. Okay. You can go more general if you want, but then you will have assumptions, kind of abstract assumptions you will have to check in practice. And I believe it can be checked in many cases, and I will come back to this later. So bounded risk aversion, actually, what we really need for the proof is upper bound, big R. You will see it in the proof. The lower bound here is to be sure that we have existence in the dual problem. So we have dual martingale measure. And this is used only if you are in incomplete market, because if you are in a complete market, you don't need this lower bound to ensure that the dual problem is well set and you have existence of a Lagrange multiplier. Okay, so it's only in incomplete market that, well, it's more comfortable to put this lower bound. We don't have to redo everything. And we can rely on what was done for incomplete markets before to have existence. But again, if you are in a complete market, you just need a upper bound. Okay, so because we have this lower bound in general, the admissibility conditions we will put for the utility maximization problems are the usual one, and they correspond to the case where the utility function is of exponential shape. This means that we, in the frictionless market and in the market with transaction cost, we say that the Wells process is admissible if it is super martingale under any absolutely continuous martingale measure with finite entropy, which is a good framework to work with in this setting. Okay, so if you have this, including the lower bound, you know that you have an optimizer for the problem without transaction cost, and that there is an equivalent martingale measure for the stock price. And as usual, the optimizer in the primal and optimizer in the draw problem are related by this. So the derivative of the utility at the optimal wells is up to constant. The density of the dual optimizer with respect to the original measure P. Keep this in mind for later, but this is as usual, okay? Okay, so now let's do the proof for obtaining the bound. Okay, so the proof is really what you want to write, and what is written, and usually, including in the paper by Mathieu, Tonkov, and Kai, they say at a point, well, and if we have blah, 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 then this is good. So we just complete the and if we have. But this is exactly what you want to do. I mean, you do the simplest thing. You have, so delta is difference between utility in the model with transaction cost and the guy without transaction cost, and here I take the optimal policy in the model without transaction cost. Okay, so I do a second order expansion. So the difference of the two is the derivative of the optimal portfolio in the Morton problem times the difference of the wells plus 1/2 the second derivative, a guy that is in between these two guys, okay, and the difference to the square. So the zeta, here, is lambda is a random variable between -1 and 1, so it's a convex combination of the two. It's somebody in between the two guys. Okay? Okay, so you really go the easier way. Okay, now, so alpha is just the expectation of u prime. Here, this is u prime over, well, divided by alpha multiplied by alpha. So look at this like u prime over the expectation, and I told you that this is exactly the density of the change of measure. Okay, so expectation u prime is the same as expectation, well, alpha expectation under the q hat. That is a martingale measure. So you get rid of this u prime. Everybody knows that this is a good way to do this. And then because I take expectation under q hat, then I have here to derive by devise by u prime. Okay, now you're quite good because, well, this guy, I have, if I use the rule I gave you before, I know how to control this guy perfectly. I know how to control the square here perfectly. So if I had a constant here, I would be this would be finished. Okay, and if you use the bounds I gave you on the tracking error problem, in the case where I just take expectation, not expectation of the absolute value, and in the case where I take the L2 norm, well, I just write down things, I equate the terms in delta and epsilon, and I have the result. So the question is what I do with that guy, and this is where there is a trick, in the case where risk aversion is bounded. So it's a very easy observation. I don't know if it has been used before or not. But, okay, u second over u prime at different points. This is u second over u prime at the same point, multiplied by u prime over u prime at the different points. Okay. This guy is bounded, minus this guy is bounded by R. So this guy I control it by R. This is a minus R I have here. Okay, this is my assumption. Now u prime over u prime. U prime over u prime. So if you take the derivative of log of u prime, this is u second over u prime. U second over u prime is bounded. So the derivative of log of u prime is bounded. So log of u prime has linear growth. So u prime has exponential growth. So the ratio of two u prime guys, this is just an exponential. Just because u second over u prime is bounded. Okay? And again, if you differentiate log of u prime, you get u second over u prime. So u prime over u prime, this is bounded by exponential something. So now it's cool because, if I had a constant here, I could conclude, well, I don't have a constant, but I have something like this. And now the zeta minus x, this is something like lambda x with transaction cost minus x without transaction cost. So I will have lambda between 0 and 1 and the difference of the Wells process. But the difference of the Wells process, I control it. I know that this is of order of epsilon. It's going to 0. Okay? So, well, it's something like epsilon multiplied by terms, essentially. So I just have to assume that I have some small exponential moments on some of my initial ingredients, and small in the sense that as small as I want, okay? And I will be able to conclude. So let me rewrite everything. So I had this lower bound, okay? Now I control this term by this one. I just plug it here. I had one line that is what I told you. So zeta is the convex combination of these two guys. So zeta minus x theta hat, this is lambda times the guy in the model with transaction cost minus the guy in the model without transaction cost. And lambda is random variable bounded by 1. And now, again, sorry, this term is some stochastic integral, some quadratic variation, some guys, okay, but multiplied by something that is going to 0 with epsilon. Okay? So I need, again, one assumption. So I assume that this guy, and this guy that you have already seen before, well, not that one over there, they have a small exponential moment. It can be as small as I want. Okay? When epsilon is going to 0, the iota can go to 0. And this is also a difference with the work of Carlsen and Muhle-Karbe, where they had to impose a fixed exponential moment with a constant, not going to 0 with the transaction cost. Here we just need as small as you want exponential moment. Okay, and if you have this, well, this is what I wrote before. Now this is very simple. This guy, I control it. I gave you the control already. This guy, I control it in any LP. So I do a small order, okay, to obtain a L2 eta norm here, something like that. And with respect to the iota that I have here. And this is what we get. Okay, maybe I don't enter into details. But anyway, if you put everything together, so this is a term that is controlling this guy here, multiplied by epsilon. So epsilon times this is the term that is controlling this guy. And this is, so I did an order on this. So obviously you have to assume, well, if you have exponential moments anyway, the assumption on the LP norms of the guy that I put before will be satisfied automatically. So I just do a little order with respect to this iota over there. And then you just use the bound I gave you before, and you will see that the difference of expected utility, if you take, so I didn't rewrote all the terms here, but if you take delta equal epsilon to the power 1/3, is actually controlled by epsilon to the power 2/3. So you see this is very, very simple, and I use the simplest way to approximate the optimal strategy in the model with the transaction cost. Okay, so in practice, what you can do if you have, for instance, a model, you are within a complete market, say, so things are more or less explicit in the model without transaction cost. You add transaction cost. What you do is just take what you would have done in the model with transaction cost. You put a buffer of order of epsilon to the power 1/3, and you transact only when you reach this buffer. And this will be something that is optimal in the model with transaction cost up to this power. Okay, you cannot do better. Okay, yeah, in particular, the SIP of the difference is what you want. Okay, so you cannot really do better. I mean, the other inequality is trivial. I still have a bit of time, right? Okay. Another thing that, so maybe people know it, but it's also not written. So, I mean, if things have been known by some of you, at least this is kind of teacher's note where we write down things. Okay, you can take it like this. But another thing that is quite surprising is, because now, I mean, still I had some assumptions, okay? I assume that the optimal strategy in the problem without transaction cost is like this. So, well, you can, in the PDE papers, they put assumptions on this guy that are quite strong. And this has to go up to the boundary, capital T, in the more general papers, and this is something very difficult to check. I mean, unless you are in the Black-Scholes model and you know that the optimal strategy is a constant or something like that. But still, well, you have to check this. So let me show you one way to check it, at least in the case of a complete market, which from a numerical point of view is really the case where you will be able to do things at the end, okay? Because apart from certain incomplete markets, this is essentially incomplete markets that you know the optimal strategy in the frictionless model, okay? So let's stick to the diffusion complete market. So all the coefficients are nice. Anyway, I will put, well, actually I'm putting assumptions. So again, these assumptions, this is just to have everything simple to write, okay? You can redo the proof and change the estimate if you want to have more general assumptions. Okay, so let's put some assumptions. Anyway, I won't do the proof because it's basically only computations, but it's like 2 or 3 pages. It's straightforward computations, but you have to make them. Okay, How can you check the assumption we made on theta? So there are two kinds of assumptions. Assumptions on S, but this is an ingredient of the model, so you assume it, okay? And then assumptions on the optimal strategy theta hat. This you have to check it, okay? At least in terms of S or something that is an ingredient of your model. Okay, so the optimal strategy, that should be that here. The optimal strategy, U prime of the optimal strategy is up to constant the change of measure. And here, because I am in complete market, I know what the change of measure is explicitly. Okay. So the optimal strategy is U prime minus 1 of the change of measure. Okay. Now this guy, this is integral of theta ds. So if S is this swarm, forget about the drift. This is integral of theta sigma dw. Okay? So if you take the time t Malliavin derivative of this guy, you will actually obtain what is here, theta sigma time t. Or not exactly that, but at least the Clark-Ocon formula will tell you that the guy that is in the stochastic integral representation of the terminal Wells process, the guy here has to be, by the Clark-Ocon formula, this has to be the expectation under Q hat of the time t Malliavin derivative of the terminal Wells given ft. This is just the Clark-Ocon formula. Okay? So this way you put your hand on the optimal strategy. This is why it's more or less explicit in complete markets. More, at least from this point of view, you see that at least you have a formula. Okay, now sigma is invertible. You put bounds on it, so you really have theta hat. What you have to control now is this guy, the Malliavin derivative. But the Malliavin derivative, this is not difficult to estimate, because you know what the terminal Wells is. It's U prime minus 1 of the change of measure. And the change of measure, you know it. Okay, so you just compute the Malliavin derivative and you do estimates, blah, blah, blah. And this is really not difficult. And this will give you that theta is bounded with these assumptions that are very strong. If you want to have linear growth with respect to some guy, then theta will have linear growth, etc. Okay. Here with this very strong assumption, theta is bounded. Now, here you have a formula for theta, but we have also an assumption on the bracket of theta. So I have to go to the volatility of theta. Okay? So to go to theta, which is the volatility of x, I use the Clark-Ocon formula on x once. If I want to go to the bracket of theta, I have to apply the Clark-Ocon formula on theta itself. So I have to go to the second order Malliavin derivative. But you just do it. You take Malliavin derivative twice. Okay, and then you do LP estimates, very, very standard one. There is no trick, it's straight. So again, if you put these very strong assumptions that you can certainly relax and have linear growth instead of boundedness or other types of growth if you want, well, you will end up with the fact that, well, theta is bounded. It has an Ito decomposition of this form. And in this decomposition, alpha and gamma are bounded. So in particular, the bracket is bounded. So the exponential moment exists, everything is well defined. So again, in the paper, we don't try for the maximum of generality, okay? Because if you allow for linear growth of this guy, then the estimate will be a little bit more difficult to make, longer, it will take more pages, and we just want to say, okay, it's just use the Clark-Ocon formula and you just check everything. It's you don't need to go to PD estimates or something like that. One other point I would like to make on the level of generality of this paper. So certainly here we don't have to take care of the fact that the Wells is positive or negative because utility is defined on the Orwell line, and this is a very important point. I mean, if you want to have utility functions defined only on the positive line, you will have to control the fact that your Wells, the Wells I construct here, doesn't go to 0. And so typically you will stop it at a certain level before 0, and you will have to estimate the time where you stop it, etc. This is another story. I don't want to enter into this. But on the other hand, this ratio here, I use the fact that I have bounded risk aversion to control these guys into this guy, okay? A more general assumption will just be to say, well, just say I have a control of u second over u prime by a certain function, okay, that have in the formula the difference of the two guys here, and well, yeah, you see what I mean. You can put an abstract assumption if you want, and if you have utility functions that satisfy this kind of bounds, you can just use exactly the same arguments. Okay. So I thought that I would be shorter, but I will stop in 2 minutes. Now, yeah, what I told you from the beginning is that, well, at least from my perspective, the most common model is not, with transaction cost, is not the one I have presented you. It's more a model where transaction costs are put on the amount of money you transfer when you do transactions. Okay? And then the model I showed you is not doing that. Again, it's doing the case where you pay transaction cost proportional to the number of stocks. If you imagine a beta spread, okay, it's more about the amount you transact rather than the number of stocks. It's really transaction cost with respect to the amount. Okay, now if you want to do the amounts, it's the same, but a little bit more painful to write. So here I will assume that the stock price is strictly positive component by component. And now in the frictionless model, theta is the amount of money I put in each of the stock. So theta divided by S is component by component. This gives you these are amounts. So this is the number of units you have in the different stocks times the variation of the stock. This is cool. And now for the case with transaction cost, well, if you want to work with amounts, it's better to write it like this. So here the Y will correspond to the amount of money you have invested in each of the stocks so far. Okay? So the dynamic of your wealth process is amount of money you have invested in the stock so far divided by the price of the stocks. This gives you number of units times the variation of the stock price. And this is here the variation in terms of amount of money invested in the different stocks. So now, when it increases, this means that you put more money in the account invested in the corresponding stock. So now transaction cost is with respect to amounts. Here, this is for final liquidation. It's the total amount of money invested in the stocks. Okay. Yeah. And what is the dynamic of the amount of money invested in the stock? Well, the amount of money that you have invested in the stock so far is related to this stochastic integral because it moves. This is an amount of money. So you see, if I have $10 invested in Alcatel and Alcatel is making plus 10%, then I have $11 invested in Alcatel. Okay, so it moves with the stock price. So amounts divided by price gives you the number of units you have times the variation of the stock price, plus what you add. Okay, what you invest. Okay, so this is how you should write the model. And now the square root problem becomes the following. It's very clear. And what you want to track mainly is the stochastic integral, okay? So what you have to track is theta with respect to y, okay? So now you will solve the square root problem. You will try to find var theta such that theta minus y remains in minus delta delta, okay? And again, you have variations of y, of var theta only when you reach the boundary of this square. Okay, so I stop here because I think I don't have any. Yeah, I have one more line. But this is exactly the same. You take the text function I gave you, phi, you remember? Okay? You do Ito lemma on theta minus y divided by delta. The only difference is that you will have more terms. It's longer to write. Okay? Then you put the good assumptions. And again, on the bracket of theta, things like that. Exactly the same kind of assumptions I gave you. The difference is that now you will have terms like the cross bracket between S and theta. These kind of terms will show up. But in the philosophy, it's exactly the same. You will just need to put different assumptions. Okay? And it's exactly the same, and you will have results that are as sharp as what I showed you before, in the sense that you cannot put less assumptions than what I did to obtain LP bounds and bounds on utility maximization problems. Okay, thank you very much. Here is part of the references I quoted during my talk. Thank you very much.
Do you have any questions? Yes.
Yes, I have two questions actually, if I may. The first one, so I'm not that familiar with all this utility thing, but I don't understand why exactly you absolutely want to have something in epsilon to the 1/2 or epsilon to the 1/3 in the first part, because it looks like in the end you get something in delta and in epsilon.
Yes.
but you can actually make the difference as small as you want by taking another delta. By taking
No. You have delta in the bounds. You have delta, and later you have 1 over delta.
right. Okay.
No, you really have to balance
if
the
you
two
take delta
terms.
larger, then the band will be epsilon or something like that.
Typically, and you have.
I mean, why does it actually matter to have epsilon 2/3?
Well, it's like this. Look, you will have epsilon. Okay, let's look at the term. You will have epsilon here times delta. This is fine. This is a constant. This is okay. But here you have epsilon over delta.
Okay.
Okay, so you have a term that is here epsilon plus epsilon over delta. These are the terms. And this one, this one. Because you don't take the delta, you take in the case where you look at LP tracking error. So, but you will have similar terms in that, guys. Okay, and then you will have terms in epsilon, terms in delta, terms in epsilon over delta with certain powers. And if you choose a balance between all these terms, you see that you take delta equal epsilon to the power 2. So, anyway, you cannot put delta to 0 just because you will transact. I mean, from the math because you have 1 over delta. And from the ID, because if you are too close, you will transact too much, and you will ruin yourself just by transacting and paying transaction cost in what you do. And yeah.
And my second question is tiny detail. So yes, I think it was somewhere here. You assume that you have these exponential moments. But it seems like you don't need to assume that. If you know that u prime over u, that basically u has, doesn't grow too much, then this exponential bounds are only needed to bound the ratio u prime over u prime, right?
Yes.
So if you could replace that by some other assumption on u, right? By saying u prime doesn't grow too much.
Yeah.
Because zeta and x hard are close anyway.
Exactly. This is what I said. Because the proof is quite simple. We wanted to keep the paper very simple. And in the case where you have bounded absolute risk aversion, it turns out that you have very easy control on this guy, and this is fully transparent. But obviously, this is the only place where I use that I have bounded risk aversion. This is the only place. So if you have any other assumptions that give you a control on the ratio of 2 u primes, in terms of the difference of the wells, this is what we have. Just use it, yes. It can be much more general. But yeah. We restrict to this case just to be fully transparent and not have kind of abstract assumption. Yes.
Okay, so this method gives you the right rate of convergence somehow. But then, so the strategy that you're using is not the optimal in epsilon.
Well, it will be optimal up to the power epsilon, 2 epsilon to the power 2, so automatically.
If you want to also catch the epsilon over 2/3, you would have to change the coefficients with the delta that you use.
Yes. Just to comment, so you can see it from the shadow point of view, or you can see it from the PD point of view. If you read the PD, in principle, it gives you exactly the shape of the delta.
Yes.
Yes.
So this is what I wanted to ask you, because you can also do it for multidimensional. Okay, so you get the corrector equations. They also work in the multidimensional.
The assumptions.
Because the shape that
they have to assume in dimension 1 you have existence essentially for free, blah blah blah. In the multivariate case, there is the other paper, and it's much more complex.
Yeah.
And
even the shape of it's not going to be a rectangle.
No, and to prove, I don't remember exactly, but either they put really strong conditions, or they just assume that there is a solution to this problem when they want to check the bounds. Because the shape is very complex. This is, and this part, honestly, is very, this part when they need to verify that this is a good order, that this is a good order, it's really, it's really sharp. So you have the PDE that is, in principle, giving you what you have to do, exactly. But sometimes if you use exactly what is in the PDE, it doesn't work. You cannot manage. So you have to twist it. So depending on the case, sometimes you exactly use it, sometimes you twist it. So in principle it gives you, but in practice it's quite complex.
Any more questions? Well, I actually have one. It's a little bit about the pain when you were that we were discussing at the end when you change instead of the cost depending on the units. But actually, is there any pain? Because in a sense, suppose that you are having foreign exchange and you're trading between dollars and euros. It's just a question of whether you are doing it in euros or in dollars. And then you just change all the notation in all your calculations and you get the other result.
Maybe, yeah, in that case, maybe. Yeah. Maybe for a fix.
So
otherwise, saying is that it's a pain. You see just that the equations are bigger. Okay. So when you apply Toslemma, you have more terms. And it's more complex, but it's just that you have 2 or 3 more terms. It's not a pain in the sense that in principle it's not more difficult. It's just longer to write. That's all.
Okay. Right. Let's thank Bruno once more.